I've been meaning to get to this project for a while. So there's a power supply I made when I was a teenager, I think, back in New Zealand. And the thing I liked most about it was this case. This is a pretty nice case. So when I moved to the US, I had an intention of just changing the transformer over and then running the same thing, but on 120 volts instead of 240. So I put this Radio Shack transformer in it, but I think that's as far as I got. The old power supply was mostly discrete components, had some large power transistors on the back. So I want to redo this. The nice thing about it is it's a dual rail one, good for doing OpAmp and type circuits, and I had the ability to switch the positive and negative rails so they're at the same voltage. I don't think it had current protection, or it didn't have variable current protection in the old one. And for what I'm going to use it for, which is really just for playing around with op amps, I don't think I need it this time as well, or I can use other power supplies for doing things where I want to play around with different current limits. So what I'm going to do, I'm going to take this whole board out. I'm going to change it to using a LM317 and 337 for managing the positive and negative rails. That's going to be kind of the easiest way of doing it, and it was probably something that wasn't available when I built this back in the early 1980s, maybe 1970s. So I'll do that, and that'll make this board a lot simpler. But otherwise I'll keep the same controls. I want to have voltage adjustment for the positive and negative rails, but also have the ability to lock them in so that I can just voltage adjust them so they're the same or balanced just by changing one control when I switch that switch. Otherwise, this amperage meter was here where I could just switch it to monitor either the positive or negative rails. I'll just leave that the same. So let's see how we get on with modernizing this, and I'll probably also take the heat sinks off the back. I think I'm not looking to put much current through the LM317, so I think I can just put some internal heat sinks in here for the amount of current that this will use for what I'm going to use it for, which is just playing around with fairly simple op-amp types. So I took the parts out of the power supply case. So you see here, I keep the mains power and light here. I'm going to keep the two holes for the potentiometer for the plus and minus voltage. I'm going to keep this switch here, which turns on tracking for the power supply, so it keeps the positive and negative voltages the same, whatever I set the positive voltage to, and still have the large hole for the meter. I kind of like that analog meter, and then the output for the display. So let's have a look at what I'm planning on doing. So I put my plan into our checklists application. There's a whole series of videos on this, but just another little application I wrote to keep track of tasks as a checklist. So I've set up a new checklist called Dual Tracking Power Supply, and these are the tasks. So review the old hardware, develop requirements for the new PSU, initial design for the power supply unit. I want to validate the design, so that's probably most of what this video will go through as I get through each stage of the power supply, going from the transformer through the rectifier to the capacitor and on to the LM317, so on, how I'm going to check that the design's actually working the way I want, and then putting that validated design, actually building it, putting it into the case, and then doing some tests on the actual power supply. Let's have a look at this first task here. So this is the requirements that I put together for it. So I want the power supply to provide dual stable low noise power rails going from plus or minus 2 volts up to about 12 volts. I only need it to deliver up to 1 amp of current on each rail, probably even less than that. I'm just going to be using it for playing around with op-amp circuits, so probably 500 milliamps will be plenty. I want to make sure the power supply unit is protected against short circuits and overheating. There's current limiting that I'll have in it, but it won't actually allow you to adjust the current. I don't think I need that for the way I'm going to use this, which again is just for fairly simple OpAmp circuits. I'm going to reuse the old case and the components where possible. Also want the user to optionally be able to select that they want to track the negative voltage to the positive voltage, and I want to be able to monitor the current draw on both the positive and negative rails. So I think that first task is done. I've reviewed the hardware, I've put together requirements. Now the second part of this is to do the design for the PSUs. Same thing here. I drew up a design and draw IO. Okay, so I'm planning on using LM317s, LM337s for the positive negative rail. So these are fairly standard voltage regulators. This really just follows fairly standard LM317 design, basically what you see on a datasheet for that. So I'm going to use a bridge rectifier to get full wave rectification of the voltage coming in. Again, I'm using that Radio Shack transformer, which gives me plus and minus 12 volts RMS around a center tap. I'm going to have a main capacitor to remove the ripple from the half wave rectifier, and I'll go through how I selected that. Then this part of the design is kind of the standard design for LM317 circuit, where you're tracking the using a variable resistor to change the voltage. And then this last part here is these LM317s need to have a constant current load on them to be able to regulate their voltage properly. They need it, I think, around 10 milliamps. So I'm going to use an LM334 to do that. And as I go through prototyping this design, we'll have a look at how each of these stages work and what we're seeing for voltages and why you need these things. Then for the negative side, basically the same design as the LM317, but using an LM337, which works exactly the same way, but for negative rails. The only tricky thing here is I want the ability for the user to switch from independently managing the voltage on the negative rail to just tracking to the positive rail. I thought of using I could set this up to actually supply a voltage here to both units from an OpAmp that would duplicate a voltage, but then I'd need to have a stable power supply for that OpAmp to make sure the voltage stays stable. So seemed a lot more work than I really wanted to go into. So what I'm going to use is a dual ganged potentiometer. So when you switch into the tracking option, it just tracks the two variable resistors on that single dual ganged potentiometer to track the two voltages. I think that's about it, and then I still need to work out the circuit for be able to switch the that 500 milliamp meter onto both the positive or the negative rails. So let's have a go at putting this together on a breadboard and looking at what's happening as I build this thing. Okay, this is where I prove out my design. So I'm going to build it up on this piece of breadboard here, and then when I actually build the real one, I can use this PCB, which is breadboard like. So transfer the design from here to this should be fairly easy. Here's my circuit diagram. I'm going to run sort of build it from left to right. So let's first have a look at what an oscilloscope shows as the waveform coming in from the secondary side of the transformer. So I've got channel 2 connected up here, channel 1 connected up between here and here to see the full wave rectified voltages, and let's just have a look at what that looks like. So let's turn it on. Okay, here we see the oscilloscope traces. It's much as you'd expect. So channel 1 is in yellow, channel 2, which is on the transformer secondary, is in purple. The transformer secondary has got a swing of 40 volts peak to peak, and then we see after the full wave rectifier that's dropped to 20 volts peak to peak. it's kind of what you expect for the frequency as well. Before the full wave rectifier, it's 60 hertz coming off the mains voltage, and then 120 volts, 120 hertz after the full wave rectifier. I use this website, Electro Schematics, to work out the details of what size capacitor I need. I won't go into the details here, just let the website walk you through it. I'll show you the calculation, but I ended up seeing that I needed a capacitor around 4,700 microfarads to do what I wanted to do with smoothing the output from the full wave rectifier. I'll put the link to this website in the description below. So I updated my circuit diagram, so it shows power supply smoothing capacitor at 47,000 microfarads, and using that calculation from the website, the delta V that you require is equal to 0.7, which is based on, with a full wave rectifier, 0.7 of the time it needs to deliver stored current to the rest of the power supply. I is the amount of current it needs to supply. In my case, it's a maximum of 1 for 1 amp. And then put in the values for capacitance and the frequency on the full wave rectifier, which would be 120 hertz, we just saw. And plugging in all the values, it shows me that with a 4,700 microfarad capacitor, I should see a ripple of about 1.24 volts, which is very doable for managing the rest of the power supply. Okay, now I'm going to test out whether my capacitor value works. So I'm using a 4,700 microfarad capacitor, and let's just put that across there first and have a look at what that looks like in the oscilloscope trace. And it's looking fairly smooth. I'm getting about 400 millivolts ripple in it, and it's showing a voltage of 18 volts out of that. Let's turn that off. Now I want to test it under load, so this is the exciting bit. So first I'm going to use about a half an amp load. So I've got 4 10 ohm resistors in series, which should, across about 20 volts, should use about half an amp of current. Let's turn that on, see what that looks like in the oscilloscope. So now we're seeing more ripple. We've got a 800 millivolt of ripple, and the voltage maximum's dropped down to 17 volts, which is all very reasonable. And we'll do one more test with a full 1 amp load on it. So just 2 10 watt or 10 ohm resistors in series should consume about 1 amp of load. Let's turn that on, see what that looks like. So more ripple, 1.2 volts of ripple. The voltage maximum's dropped down to 16 volts. Remember, we've got another probably 1.7 volts of voltage drop across the LM337, which means I should be able to regulate voltages up to about 14-15 volts, which is fine for running OpAmps, which means I can have a plus or minus maximum voltage on my rails of about 14 volts. The next part of the circuit I want to test out is around the LM317, the voltage regulator. And main thing I want to do is check that I get these 2 resistor values correct, the R1 and this 5K, it's an R2. And I'm doing that based on the data sheet, the links down in the description below, for the LM317. And this is the formula they give you for working out, based on the values there for the resistors, what the voltage out would be, and with the potentiometer at the maximum resistance would be, I'm using a 5K potentiometer, I wanted to work out what value I should have here to give me about a 15 volt top power supply, maximum power supply. So using this formula here, I put in these values. The main one I had to check out was this R1 value, and a bit of trial and error. It worked out 470 ohms should be about right. So I popped that into the formula and gives me, it should produce a maximum of 15.04 volts when there's resistance at the maximum value. When the resistance is down at 0 ohms for R2, basically it should put it down to that minimum voltage of 1.2 volts. So let's try that in our test circuit, see how it goes. So this is set up to test out that the LM317 circuit that I'm using. So in this case, instead of using the transformer and the full wave rectifier and capacitor to get the input voltage, I'm going to use a power supply, just because I want to use current limiting on my power supply in case I blow something up here. It goes into the LM317. It's been adjusted between this resistor, which would be the R1 resistor, and this R2 variable resistor, which is 5K. And let's look at the range of voltages. So I'm going to turn on my power supply, which is delivering 16 volts, and you see with this at the maximum resistance I'm getting 14.59 volts output. If I turn this around to the minimum, it's going down to 1.2 volts, which is kind of what I'm expecting for LM317, and I can vary it right through the whole range here. So that's looking good. Only thing that could improve it is it'd be nice to get it up to 15 volts. So what I may do is just add a small resistance in series with this 470 ohm resistor, just to get it up a touch to be able to deliver a maximum of 15 volts. That will depend on what happens with the ripple and things coming off the actual power supply, whether I want to go that high. I may not even want to go to 14 volts. So I'll do some experiments with that, with the actual full wave rectifier in place and some actual load on it, and as long as I don't get any ripple coming through at 15 volts, then I probably will adjust that resistor there. Okay, here's a weird problem. So in this case, let's measure the voltage here. So this is going into 60 ohms. It says it's delivering 8.4 volts there, and for my power supply it says it's delivering 0.14 amps. So that's all good, but what we want to see is when the load changes, the voltage regulator part of this should still regulate the voltage. So let's change this so it's delivering to 20 ohms. And you see the voltage has dropped down to 6.8 volts, so quite a drop in voltage. It's delivering 0.33 amps, as you'd expect with a higher load. But the voltage shouldn't change. The voltage regulator is delivering 17 volts still. The voltage regulator, I've set the current limit to 1 amp, so there's plenty of current headroom. So something's going wrong here. A voltage regulator should do what it says, regulate the voltage across different loads. Okay, this is a couple of days later. It took me a while to work out what the problem was, why I wasn't getting regulated voltage. I swapped just about everything out, the LM317s, the capacitors, the resistors. Nothing seemed to solve the problem of the voltage changing under load until I changed out the actual breadboard. So now you see I've got 20 ohms load there, it's delivering 9 volts. And now if I swap it out to 60 ohms, and we're still getting about 9 volts. So this seemed to have solved the problem by actually changing out the breadboard, and the clue to this, I'll show you the link to a blog on the internet where someone was having the same problem, and it turned out to be you need a decent breadboard for doing this power supply testing. This is the old one. This new one's seems to be a lot better built, so there must be some weird resistances happening in the cheaper breadboards. Okay, I got most of the prototyping done, so let me turn on the voltage coming into this voltage regulator. So it's got 17 volts coming into this voltage regulator, and now I was just tuning some of the resistors and setting up this constant current source at the end. So there's the voltage that it sees on the output, and I can see when I vary this variable resistor R2, it varies over a range from about 1.4 volts up to about 14 volts, which is good. And the other thing I did is I wanted to, you see here in the spec sheet for the LM317, there's a minimum load current required for the regulator to do its thing. It says here it needs to be a minimum of 3.5 milliamps typically. So I'm using one of these LM334s, which is a current source, really just a current sink. There's the pin out there, but basically you can put a resistor between this R pin and the negative pin to say how much current you want to sink under different voltages. So I've put a resistor in there, I think it's 33 ohms, and it ends up sinking 4.68 milliamps over any voltage. So you see as I adjust the voltage here, still getting the same current being sunk on the output. So that should maintain that minimum load to maintain the voltage regulating. Okay, just the last piece of prototyping here. So I've connected up the pieces for the negative side rail. It's really just a mirror image of the positive side rail, except it's using that LM337. All the same layout of the components. So let's feed it with 17 volts, and by varying the potentiometer here, you can see I can get the full range up to 15 volts again. So I think we're ready to put it onto a PCB and then put it into the case. Okay, just checking my layout before I go too far with soldering things on this this PCB board. But it's laid out just like a breadboard, so it's easy to translate my design and what I've been testing. I'm going to put the full wave rectifier bridge and the two smoothing capacitors down this end. I'm not actually going to build them on until the end of this build. I'm going to test it out with a regulated power supply first. The two regulator ICs, the LM317 and 337s, these are them here, the adjustment pins on pin 1, so it's oriented to this right hand side of the board, which is where the power output and the constant current source will be. So I've got plenty of room for all that, so I think I should be good with this. So I'll just start building this side, test it, and then connect it up to a transformer after that. So I'll just test out my PCB build here. I've got everything built except for putting the rectifier and the smoothing capacitor on there. So applying my power supply, I'm getting 15 volts output. It's using 0.005 amps, and I can adjust it through the potentiometer here. So it looks like everything's working on the positive side. Let's try the negative side. Okay, the same test on the negative rail. Swap the voltages and things, and let's turn on the power supply. So I'm seeing 15 volts on the negative side, and I'm getting the same swing. I'm getting the same amperage coming out of my PSU 0.005, so it looks like the constant current source is working fine as well. So everything's ready to put in the box. So I'm making progress with the power supply back there. I've got the potentiometers in, wired up. I've got the PCB in. All seems to work. I just need to wire up the transformer. So the next challenge is to get the old ammeter working, and I worked out a circuit that's kind of the easiest thing to do. So I'm going to use a 4-pole switch to switch between having the ammeter measure the amperage going on the top rail or the bottom rail. So let's have a look at the circuit. I drew this one up in Lucid Chart. Kind of show the top positive rail in red, the bottom negative rail in blue. And the tricky thing here is to get the ammeter to switch between measuring amperage by going in line on the particular rail it's measuring, or allow that rail just to get pass through the power. So I'm using the switch combination. So remember, I've got a 4-pole toggle switch, and if I'm measuring voltage on or amperage on the top rail, which this indicates at the moment where the switch positions are, basically I don't let the power to flow along the top rail. I divert it so it goes down into the ammeter and measures the current going through it, and then out to the load. Then the same thing happens when I switch the switch down to negative. So in that case, the power just goes straight through the top rail, doesn't go through the ammeter at all, because these are switched over to the left hand position, and instead the ammeter is measuring the power that's going through it, but in the reverse direction. So the ammeter still shows a positive ampage. And same thing when these switches all switched, the diverter that takes the current straight through the rail gets turned off, so it has to go through the ammeter. So it's beginning to look a little complicated for wiring up my switch. So this is my switch with all the contacts on it. So on my original diagram here, I just put labeled where these various lines will enter the switch. So there's 6 things that enter the switch: 1, 2, 3, 4, 5, 6. And then I drew up this little diagram of what the back of the switch will look like, and the contact layouts, and what needs to connect where, and where I can bridge things on the switch. So that should make it easier to wire it up without making a mistake. Okay, getting near the end here. So I got most things wired up. I actually did some tests with the transformer in here, and the voltages and things seem to be good. I did have, don't look too closely at the transformer wiring yet. I did have one piece of trouble with this meter's about 55 years old, and it's kind of feeling its age. The meter's not in the actual needle's not in the right place. It wasn't working at all, so I had to get a cool new ammeter. It looks a little bit better. It's actually black down there. I got a 1 amp one, and just need to wire that in, and then I'll do the final set of tests to make sure this whole thing's working. I think the other thing I need to do is for the wiring, I just need to put a fuse in coming from the mains as well. Okay, it's testing time now. So I've cleaned up the input to the transformer, got heat shrink tape on all the important parts. I've got a 1/2 amp fuse on the power coming in. I glued the circuit diagram to the top of the lid here in case I ever come back to this and have to remember what I wired up. I also installed some current protection, but really just the simplest I could, just some 1 amp fuses here on the output rails. I actually practiced with this a little earlier, and I burnt out this LM337 when I had a short on the output here. I thought these were meant to be short circuit proof, but I guess they're not, so that's why I put these fuses in here on the output lines to blow here rather than blow the voltage regulators. Otherwise I've hooked everything up, got the ammeter switch here, the tracking switch here. I'm going to try this out with some load. So on the positive rail I've got 20 ohms load, and then on the negative rail I've got 40 ohms load. I'll show a bit later in the video what it looks like on the ammeter with these loads, but from the top, let's turn it on. I've also measuring the positive voltage here, positive rail, negative rail here, and just for good measure I'm measuring the amperage coming into the unit, just to make sure I haven't got anything weird happening somewhere where it's burning off a lot of energy that I don't know about. So let's turn this on, and you see the positive rail's at 9.4 volt, negative rails at 10 volts. If I vary this resistor here, you see they move in sync. They're not exactly the same. I think probably the resistors down here, the adjustment resistors, I think it's R2. I don't think they're exactly the same, so probably I should have used a variable resistor, but this is close enough for what I'm doing anyway for testing out OpAmp circuits, so they're close enough in different voltages, and if I'm really worried about getting them exactly the same, I can actually manually vary the negative voltage to match the positive voltage if I put my tongue in the right place. So if I really need to get them a lot closer, but I don't think I need to do that, so let's put it back into tracking mode. You see the power being used at the moment is 0.2 amps coming into it, and if I look at the ammeter on the front here at the 6 volts, I'm seeing about 1.7 amps going into the negative line and probably 3 amps going to the positive. If I push the voltage up here, you see the amperage goes up in here as well. Probably only run this at about half an amp, otherwise I'll probably stop. And of course I've got a temperature meter here just to check on my power being used in these heat sinks. I got to about 55 degrees on the negative, 41 degrees on the positive. So again, I don't want to put a lot of amps through this. I don't think the heat sinks would cope with it. If I really wanted to get to 1 amp, I think I'd have to take these off and put bigger heat sinks on, or put a fan in here. And I'm not going to be doing any of those things, so I'm not really going to be using it at high amperages anyway. And let's have a look at the AC on the positive line with 20 ohm load, and AC on the negative line. I think that means it's pretty low on the negative as well. I'd actually hooked up an oscilloscope and I can see a lot of ripple on the negative line, so I think we're good there. I'm just going to close up and show the ammeter. So just have a look at this ammeter now. Remember, I've got it on this 4-pole switch here. I've got 40 ohms on the positive rail, 40 ohms on the negative rail. Let's turn it on, and you see positive rail shows 2 amps, around 2 amps. Negative rail shows about 2 amps as well. And let's just go up to the positive and put it down to 20 ohms, and you see it doubles in amperage here, probably 4.4 or 0.44 amps now. So that's looking good, looking like the amp meter's working fine. So I think this is good enough for what I wanted to do with it. It could be better, but this is good enough for an OpAmp power supply, and again I've got a better regulated one if I'm really doing power supply stuff. So here we go, it's all set up on my workbench now, so just put it underneath my function generator, and I've got the normal power supply next to it if I need a more regulated power supply, but that should work well for op amps.